Alright, we're going to factor special cases today. This is the 5th attempt to make this video, so let's see if it finally gets all the way completed. We got two patterns we're going to talk about. We've got difference of two squares pattern and the perfect square trinomial pattern. The key for these patterns is we're talking about difference of two squares, perfect squares, or perfect square trinomials. Trinomials meaning three terms. So when you look at having two terms that are both squared and there's a difference, you can factor it as a plus b times a minus b. With perfect square trinomials, there's three terms, and we notice that the first and last terms are both perfect squares. And we can factor them as a plus b squared or the quantity a minus b squared. So these are a little bit more tricky to see, but through example it should be okay. Number one, example one, we're going to factor 5x squared minus 45. Now 5 and 45 are not perfect squares, but there are two terms here, so immediately I want to think, ooh, difference of two squares pattern. But it's not, because those two numbers are not perfect squares, but they do have a common term. That common term is 5. So we factor out of 5, and I'm left with x squared minus 9. Now in my mind, I have to factor what's in parentheses if it's possible to factor. So when I look at that, I say, well, x squared is just 1x squared, and 9 is actually 3 squared. So now I have two terms in parentheses that are both perfect squares. So let's apply the rule. A plus b, a minus b. A is going to be 1x, or just x, and b is going to be 3. So I have x plus 3, x minus 3, and I factored my binomial here, two-termed expression. So I factored out of 5. Again, always look in parentheses to see what you can do, and this time we can apply the difference of two squares pattern. In the second example, we notice that we have factoring 9x squared minus 1, but right away I see that I have 9x squared minus 1. 9 is a perfect square, and 1 is a perfect square. So let's rewrite 9x squared as the quantity 3x squared. 1 is just 1 squared. Okay, so I've rewritten my beginning expression. I see two terms. This is a difference, and the terms are perfect squares. So I've got everything I need to use the difference of two squares pattern. Two terms, you're subtracting, both terms are perfect squares. In this case, a is actually going to be 3x, and b is going to be 1. So this factors into 3x plus 1 times the quantity 3x minus 1. And the key here is when these terms are perfect squares, you can simplify and get your a term. A is not going to be just 3. Okay? Rewrite the perfect squares when possible to get your a and b. So in example 3, we're actually going to start looking at cases of perfect square trinomials. Now factor 16y squared plus 24y plus 9. I'm looking, and 3 does not go into 16. There's no common terms. So we've learned other patterns of factoring when a is not 1, when it's greater than 1, of ax squared plus bx plus c. But this would be a pretty large product to find. Two factors whose product is this, 16 times 9, whose sum is 24. So looking to the first and last term, I see a perfect square of 16 and a perfect square of 9. 16y squared is 4 squared times y squared, which can be written as this. These two expressions are equivalent, as is 9 is equal to 3 squared. 16y squared is 4y raised to the second power. So the first and last terms are perfect squares. So I'm going to try to use this pattern. Okay, I'm using addition because all the terms are addition. So now I have to think, well great, I have my a term, I have my b term. A is 4y, b is 3. But do I get 2 times ab? Meaning if I multiply 2 times what I picked for a and what I picked for b, do I get 24y? Let's check. 2 times 4y times 3. That actually equals 24y, so I get my check mark. Perfect square trinomial says this pattern is equal to a plus b, that quantity, squared. So a plus b, that quantity, is all squared, and I factored my perfect square trinomial. We're looking at another perfect square trinomial here in example 4, factoring 9y squared plus 12y plus 4. So again, the first and last term are perfect squares. So I look at my pattern. I've got to pick A and I've got to pick B. 9y squared is also the same thing as 3y raised to the second power, and 4 is just 2 squared. Now, A is 3y and B is 2. So I put a big question mark here. If I multiply 2 times A times B, do I get 12y? If I do, I can use my pattern. So 2 times 3y times 2. That does equal 12y. I get my check mark. Perfect square trinomial says if I have this pattern, A plus B, that quantity is squared. A plus B, that whole quantity is squared. So that's the second example of a perfect square trinomial. It's very important to remember, you have to think about that middle term. So if I gave you a perfect square here, and I said this was 13, you couldn't use this pattern because you wouldn't get 12y in the middle, or 13y in the middle. You'd actually get 12. So just be careful. Always remember, whatever you pick for A and whatever you pick for B, 2 times A times B has to equal that middle term. So, in our final example, I give you another perfect square trinomial, 36x squared minus 84x plus 49. Now that middle term is subtraction, so we're going to use the subtraction sign if we can with the perfect square trinomial. Is it a perfect square? Let's see. 36x squared and 49. Well, 36 is a perfect square, 49 is a perfect square. 36x squared is actually the quantity 6 times x squared. 49 is 7 squared, and again, does 2 times AB equal 84x? Let's pick A to be 6x, B to be 7. 2 times 6x times 7. 42x times 2 is 84. We get x. Perfect. This is subtraction. We use A, the quantity A minus B squared. A minus B squared, so 6x minus 7 squared. Again, couple things to be careful. This first term has to be a perfect square. This last term has to be a perfect square. And when you pick A and B, your middle value has to be equal to 2 times AB. So whatever you plug in for AB and you double it, right, when you multiply, you've got to get that middle term. If this number was not 36, let's say it was 37x squared, this pattern would not work. This term has to be a perfect square, the whole thing, perfect square, for this to even to be considered. So that was factoring special cases. If you have any questions, just type the comment below, or you can email me at nicholas.bennett@dc.gov. Thanks.